All right, let's come back. Now we will continue our discussion on the center of mass idea. And now it is also more convenient. It will also be more convenient. We have a formula for calculating the center of mass of a composite system. A composite system consists of two or more bodies. Okay, and the position of the center of mass is known. For example, here we have a two body, A and B. The positions of center of mass of the first body is RA. For the second body, the position is RB. And when the two bodies are put together, what is the position of the common center of mass? We regard them as a body as a whole, right? So we are going to find that out. Now, first we rewrite the formula for the system, the whole object, including both of this smaller object. So R is equal to 1 over M. The M is a total mass, okay, including both objects, right? And we form a summation of MIRI. That is the summation we used before. But now we emphasize here with a bracket that the summation covers the pieces, the small pieces in both the object A and B. So the summation runs over all the points on object A and also on object B. So we write a bracket A plus B to denote that. Okay. But this is a summation only. A summation can always be decomposed, right? Can always be separate because we sum over object A and then we sum over object B, so they can be separate into two terms. The first term contains a summation over object A. The second term contains a summation over object B. So the sum can be separate into two terms. And the total mass of the system is the mass of A plus the mass of B. Is that right? Because we now have two objects, so that is of course the total mass. Now we for each of this sum, for the first sum, we divide with MA, and we multiply with MA. So we did nothing. Okay, we just divide and multiply by MA. For the second sum, we also divide and multiply by MB. Now, why do we do that? Because we want to identify this summation over the mass as the position of center of mass of the first object, that is RA. So the red thing is actually RA. And the blue thing, similarly, the blue thing is RB, right? So the summation MRR divided by MB is RB. So we now have the formula. The formula is that if you want to find the center of mass position of the composite object, then you have the mass of the first object multiplied by its center of mass, plus the mass of the second object multiplied again by the center of mass, and divided by the total mass of the system. So you can see the formula just looks like if the two objects are 2-point mass. You just use the center of mass position of the two objects, and you form a sum, just like the center. You find the center of mass of 2-point object, and you find the center of mass of the whole system. Okay, so that is an easy extension of the center of mass concept. Now we should use this try to use this formula to calculate the center of mass of this lamina. Again, a lamina on the XY plane. The lamina consists of a square of side equal to A, and an equilateral triangle with a side equal to A, and the triangle is at the top of the square, and square is now placed on with its base placed on the x-axis. Okay, so we want to find the heights of the center of mass of the composite object above the x-axis. Now, first we look at the area of the triangle. Now, the side of the triangle is A, right? So the height of the triangle, because it is an equilateral triangle, so the angle here is 60 degrees. Each of the angle is 60 degrees. So the height is the sine multiplied by sine 60 degrees. Sine 60 degrees is square root 3 over 2. So the height is square root 3 over 2a. The area of the triangle is, of course, 1/2 of the heights, of of the heights multiplied by the base. So 1/2 HA. H is square root 3 over A. And we also have another A here. And so the area of the triangle will become square root 3 over 4A squared. Okay. Now the center of mass of the triangle is at centroid. The centroid position is at a height of h over 3 above the base. So this height is h over 3. But we now count the heights from the x-axis. So the heights of the triangle of the center of mass of the triangle above the x-axis is h over 3 plus a, where a is the height of the square, right? We add the height of the square to the heights of the centroid above the base of the triangle. So we got this number. Okay. Now we are ready to find the center of mass of the composite object. Now the area of the square is trivial, is a square, right? Simply a square. The height of the center of mass above the x-axis is of course a over 2, because for a square, the center of mass must be at the center. Okay. So now we have MAYA plus MBYB divided by MA plus MB. MA is proportional to the area, right? The area of the triangle. You can multiply by density, but the density will eventually cancel on the numerator and the denominator, so that doesn't matter. You can take the density to be 1. Okay. The area of the triangle is this, right? And the height of the center of mass, as we calculate, is this. The area of the square is a square, and the height of the center of mass above the x-axis is a over 2. And the total area, total mass of the two objects is proportional to the total area. So it's equal to the area of the triangle plus the area of the square. And after some simplification, we find the position of the center of mass to be given by this. Okay. So that is a simple example which illustrates to you how to calculate the position of center of mass of a composite object. Now we want to prove an important theorem about the center of mass, and that is the center of mass is independent of the coordinate we choose. That is important. Now, why that is important? Now, when you look at this formula, summation MRI divided by M, you may wonder, since the coordinate is chosen by us, it's arbitrary chosen by us. If you use R, which is depending on the coordinate we choose, right? Ri must be depend on the coordinate we choose. If you choose a different the position of the coordinate origin, then you have a different Ri. And so you may wonder, if the summation MRI divided by M that is given by this formula, is it independent of coordinates? If I use a different coordinate origin to calculate the center of mass using different Ri, would I get the same position? Or if I get a different position? Now, if I get a different position by using, a different origin, then probably the concept of center of mass is not so useful, because it depends on what I choose. Physics should not depend on what the observer chooses, right? Physics should be something absolute. It's something independent on whatever coordinate I choose. It should not depend on the coordinate we choose. Okay, so I want to verify that if I choose a different position to be the coordinate origin, instead of I choose O here, I may choose another point which I call O prime, and I follow this formula, I still could find the same position of the center of mass. So center of mass is something that is intrinsic to the object. It is a physical property that is intrinsic with that object, and it does not depend on how I choose the coordinate origin. Can you understand that? Now, so we will proceed with the proof. Consider now we have two coordinate origin. The first origin is O, I call it O. The second origin, I call it O prime. And they are connected by a displacement vector. A vector D is from O to O prime. Okay, this is a constant vector. Now, suppose we have a piece of mass here. This is extended object, and I suppose I chop it into very, very small pieces. And for the I pieces, the mass is mi. And for relative to the original origin, O, the position vector of this small piece of mass is Ri. But relative to the new coordinate origin, which I call O prime, the position vector is Ri prime. The two vectors are obviously different, okay? I'm not talking about object moving closer speed of light. That is another thing. That depends on observer. Okay, I'm now assuming everything at rest. Okay, so everything, including the observer and the object, they are at rest relative to each other. If you want relativity, then total different things. You have to do the Lorentz transformation and not the coordinate translation. Okay. Now, so these two vectors must be different. Ri and Ri prime will be different, but they are connected by a simple equation. If you look at this triangle, you will find that Ri prime plus D is equal to Ri. Is that right? You simply follow the parallelogram rule of the tip to tail method of addition. D plus Ri prime is equal to Ri. So when you express the center of mass position in terms of the of Ri, you can convert the Ri into Ri prime plus D, right? For each of these pieces, you have this relation. Ri is equal to Ri prime plus D. But for this summation, you can separate two terms. The first term is summation mi Ri prime. The second term is summation mi multiplied by D. But the D can be taken out of the summation since it's a constant. For a constant thing, you can always take it out. It's a common factor in all terms. So you can take it out from the summation. So you now have a summation M, right? Summation Mi. But the summation Mi is the total mass of this object, which is capital M. And the capital M simply cancel with the M outside, with the 1 over M outside. And you are left with the factor D, right? You left only with D. But you look at this, the first thing. Summation Mi prime divided by M. What is that? That is, according to this formula, that is, of course, the center of mass position relative to the new origin. If I use my new origin to do the calculation, the center of mass position will be given by this. So I denote it by R prime. R prime is the center of mass position relative to the new coordinate origin. Okay, so after doing some calculation, you arrive at this. R equal to R prime plus D. The two position vector of the center of mass relative to the old and the new coordinate origin, they are related this way. But look at the diagram. If they are related this way, then what should they look like? Well, they refer to the same point. Why? If the center of mass position is here, then I point a vector from the origin to the center of mass. I call this R, right? If I point it from the new origin O prime to the center of mass position, then I got another vector R prime. You see R and R prime, if you look at this triangle, R prime and D, they are simply related to this by this equation, right? So this equation means what? Means that both this vector R and this vector R prime, although they are from different origin, but they refer to the same position in the object. So that they refer to the same center of mass position. Okay, you see this equation, R prime equal to R equal to R prime plus D, they simply form a triangle. So the two vectors actually refer to the same position of the center of mass. And so the center of mass position is independent of the coordinate you choose. Whatever coordinate you choose, although you get a different expression for the vector r, the center of mass position vector r, it always refers to the same position in the object. Okay, so that is an important thing to know. Now, in particular, if we like, we can choose the coordinate origin, the new coordinate origin O prime, to be exactly at the position of the center of mass. And in that case, R prime is of course 0, right? Because R prime refer to the, in that case, R is equal to D, right? Because R is D is a vector that points from the old origin to the new origin, right? But now D is equal to R, right? So D and R are equal. And R prime is of course 0 because now I'm at the center of mass, right? So and I'm at, when origin is the center of mass, the center of mass position is of course relative to me is of course 0. Is that right? So in that case, if you put everything into this formula, when R and D are equal, then R prime is equal to 0. Now the physical meaning is very obvious. You calculate the center of mass position while you are while your origin is located exactly at the center of mass. So of course you get 0, right? Is that right? You are calculating the center of mass position, but your origin is located exactly at the center of mass. So of course you get 0. So that means the moment, if I call this summation, the moment of the object about the center of mass position, then that means the moment of the object about the center of mass position is 0. And I got this formula. Now to emphasize that, now I take the center of mass position to be my origin. I call this Ri prime. Instead of prime, I call it RICM. RICM denote the position of the pieces of mass Mi relative to the origin. Okay, so when relative to the center of mass. So there's a vector pointing out from the center of mass to the piece Mi, and I call that vector RICM. So when I form a summation of Mi RICM over all the masses, all the small pieces of mass in this object, I will get 0. So that means the moment, if I call this moment, because essentially the mass multiplied by length is a moment, right? So if the moment, if that I call this moment, then the first moment about the center of mass is 0. Now, but that is not something new. That's actually you have learned before. Now, for example, if you have two boys of different masses, the first boy has a mass m1, the second boy has a mass m2, and they try to balance themselves on a seesaw. How would they do it? Well, the answer is simple. They sit at different distance from the center of mass position, which is the pivot of the seesaw. Okay, and of course, in order to balance themselves on the seesaw, the center of mass position must be at the pivot. And we have a simple relation. M1 multiplied by R1 is equal to M2 multiplied by R2. That is a simple equation of moment. If you multiply both sides by G, that is the weight. And the weight multiplied by length is the moment, right? Now you can see it's exactly this equation. If I choose this to be the origin, and I use two vectors, that the one vector is point to the first person, the other vector points to second person. I call R1CM and R2CM respectively. Then M1 R1CM plus M2 R2CM is 0. Because the two vectors are in opposite direction and the moment are equal. So that is not something new. That is something when you are located at the center of mass position, and you find the moment of all the masses around you. Okay, of all the masses in the object, you find that summation to be equal to 0. Now then we come to the last part of this chapter, and the last part of this chapter concerned with a variable mass system. Now this is something difficult. So I put it in the extension, meaning that I will not test it in the examination. Anything I put it in the extension part. If you see there's a label here on the top of the slide, that means I put it an extension, and that extension will not be tested in the any exam. Okay, is it okay? Now, but note of learning, that's our syllabus of the midterm exam is from chapter 1 to chapter 6, including the momentum and collision, right? Including this chapter. But the mathematical skills, the calculus, the Taylor series, etc., all these things that associate with each of the chapter, the mathematical supplement that associate with different chapters, they will be tested in the exam. Okay. So the extension will not be tested, but the mathematical skills that are be taught in lecture together with the those chapter will be tested. Okay. Now Newton's second law for mass m is given by F equal to ma, right? But it's difficult to apply this system to a system with variable mass. Here we always, when we apply Newton's second law in a high school or even in a university, we always assume m is constant, right? But imagine if you have a system that has a changing mass, then you don't know what this mass would mean, because the mass itself is changing. Then you have difficulty in applying Newton's second law to the object, right? If the mass is changing. Now, what system may have a changing mass? For example, a rocket ejecting some fuel. When the fuel are being ejected as hot gases out of the rocket, the mass of the rocket is decreasing with time. So the mass itself is changing. So you don't know what the mass refers to, right? So that poses a problem. And if you have some moving cart, for example, and you drop some mass, you drop some object into the moving cart, then the mass is also changing. Now, in those cases, you cannot simply use Newton's second law of this form to handle those problems, because it actually involves more than one object interacting with each other. So you must go back to the basic principle of momentum. You have to consider the momentum instead of using Newton's second law for a single object. Okay. Now we shall illustrate it by using an example. We will not discuss about a general case. We will discuss an example of a motion of a rocket ejecting some fuel. Okay. We'll see how do we handle this by using a momentum consideration. Now we consider a rocket eject fuel at a rate of q kilogram per second, meaning that the fuel is ejected at a rate of q kg per second. Each second, q kilogram of fuel is ejected out. Okay, so that is the idea. Now, the fuel is ejected at a constant velocity, but that velocity I call u is relative to the rocket. So relative to the rocket, the fuel is ejected at a constant velocity. But the rocket itself is moving relative to an observer on the ground, right? So relative to an observer on the ground, the fuel is not ejected at a constant velocity because the velocity of the rocket itself is changing, right? So in order to describe the whole phenomena, we have to go back. We have to translate this velocity into another velocity that is relative to an observer at rest on the ground. Okay. Now the velocity of the rocket itself is v, right? That is relative to the ground. So the velocity of the field relative to the ground, you have to use the relative velocity concept. If the velocity of the rocket itself is v, and the velocity of the field is u, then the velocity of the field relative to the ground is v minus u. Now the field is actually ejected in opposite direction. Okay, so having a velocity v forward, we actually decrease we actually decrease the velocity u. Okay, we have v minus u because we define the right direction, the direction of travel of the rocket as positive. Okay, so relative to this positive direction, the velocity of ejection is minus u, and the minus u velocity has to be added to the velocity of the rocket to get the velocity of the field relative to the ground. Okay, is that clear? So we actually define like this. This is a positive direction. So minus u is the velocity relative to the rocket. And if I want to find the velocity relative to the ground observer, then I have to add this velocity to the velocity of the rocket itself, right? So that's why I add v to minus u, and I got this one, this value. Now our task is to find v as a function of time. We want to know how the velocity of the rocket increase with time. So our task is to find how v increase with time when the field are being ejected continuously. So let us use momentum consideration. At a certain instant t, the mass of the rocket is m. Now m is changing, right? M is changing with time. You notice that. And the velocity of the rocket is v. V is also changing with time. And in a short, moment later, in just a small time interval later, which is delta t, the rocket eject amount of field of mass equal to q delta t, right? Q is the mass ejected per unit time. So q delta t is the mass of field ejected in the time delta t. And it is ejected as a velocity v minus u, as we said before. This is relative to the ground. The rocket now loses a mass of q delta t, right? Because the field is being ejected. So the new mass of the rocket is m minus q delta t. That is the reduced mass of the rocket. And the velocity of the rocket may increase. It will increase from v to v plus delta v. Is that clear? Now, so we compare the initial total momentum with the final total momentum of the system. When we neglect gravity, when gravity is neglected, the total momentum initially is equal to the total momentum finally. So we equate the two momentum to get the equation of motion. Okay, the initial momentum is of course mv, just the rocket multiplied by its velocity. The final momentum is more complicated. It consists of the momentum of the rocket together with the momentum of the field ejected at that time, small time interval. Okay, because we always refer to this confined system. The confined system consists of the rocket and the field that is ejected in a small time interval. So the final momentum of the rocket is m minus q delta t multiplied by v plus delta v. That is the final momentum of the rocket. The momentum of the field is q delta t multiplied by v minus u. So we add the two momentum together, and this should give me the initial momentum of the system. This should be equal to the initial momentum of the system. Now we expand this these two brackets, and some of the term cancel, including the q delta t here. Qv delta t here cancel with the minus qv delta t. We have mv as the first term, but the first term cancel with the mv on the left-hand side. And we also have m delta v at this term. And we also have a second order term, q delta v delta t. Now we omit this term. In a minute, I would let you see why. Let me omit this term. I do not count this term, delta t delta v. Okay, and so the last term only give me a term of Q U delta T with a minus sign. Okay. Now, so most of the term actually cancel, and we are left with two terms. Okay. And the two terms are given by M delta V minus QU delta T. Is that right? Now we derive the equation by delta T. And we take the limit where delta T tends to 0. And so delta V over delta T become dV dt. And on the right-hand side, we have QU over M. Is that right? Now, but the right-hand side is not the constant. The right-hand side contains the mass, M. Q and U are constant, but the M is not constant. The M, the mass of the rocket, is actually decreasing with time. If the initial mass of the rocket is M0, then in a time t, the mass of the rocket, because of the fuel ejected, the mass of the rocket will be reduced to M0 minus QT. So this differential equation, the right-hand side is a time variable. It's depend on t. And we can prove the proper dependence into the equation now. M is equal to M0 minus QT. Now, but this equation can be easily integrated. We can move the dt to the right-hand side. And because the right-hand side is a function of time only, we can integrate it. Initial time is 0, final time is t. We assume that the rocket has an initial velocity v0, and after time t, its velocity is changed to v. So we have the final velocity as the upper limit as v. The lower limit is the initial velocity v0. Is that clear? Now, so the left-hand side, of course, give me v minus v0. The right-hand side can be integrated without much difficulty. We make a change of variable of t of m0 minus qt to this variable. So instead of dt here, in our mind we convert this into d m0 minus qt. But then we have to divide it by 1 minus 1 over q in order to cancel this, right? So there's an additional factor of minus 1 over q coming out. And the argument here in the differential will be exactly the same as the denominator. So I have d, if I call this u, du over u integrate over. So I got log u, log of this quantity. And log of this quantity, you vary at the lower limit of 0 and upper limit of t. Okay. Now the q will cancel, right? The q will cancel. When I have the t you vary at 0, I simply got m0. And for the you vary at t, I have the term m0 minus qt. And the difference between two logarithms can be converted as the logarithm of the two variables. So I have log m0 over m0 minus qt. The minus sign, for the minus sign, I revert the numerator and the denominator because the minus sign corresponds to the power minus 1 in the log. So I can revert the numerator and the denominator inside the log. But I can see that the denominator is the mass at time t, right? And the right-hand side, the left-hand side is delta v, the change in velocity equal to the ejected field speed multiplied by log m0 over m. That is the result. Now you may take a look at this equation, and you will appreciate why sending a spacecraft into space is so difficult. So as to say, so difficult, because it's very difficult to accelerate the rocket to a high speed. Now the ejected speed of the field is fixed. It may be of the order of several thousand kilometers per second at most. Okay, that is limited by the chemical reaction. The chemical reaction produces certain heat, and the heat is getting high pressure build up in a combustion chamber. And eventually those hot gas are ejected out. And so that's quite limited by the chemical reaction you have, because of that that limits the maximum temperature you have, and also you have a limit size of the chamber, and that determines the ejector speed. But you can see the change in velocity also depends on what? The logarithm of the initial mass to the final mass. The logarithm is a slowly varying function. Now, this is a natural logarithm, but think about a logarithm with base 10. If you have logarithm 10, then you get 1, right? If the argument now increased by 10 times, logarithm 100, you get 2. If you have logarithm 1000, then you get only 3, right? So that means the logarithm is a very slow increasing function. You got the argument increased by 100 times, but the logarithm only increased from 1 only to 3, which is very small increase compared with the argument itself. So even if you have the mass of the rocket much larger than the mass of the spacecraft that you are going to eject into space, the rocket will be and the field will be ejected out. They will be disposed after the rocket goes into space. You only have a small part, the spacecraft that is goes into the orbit. But even if you have the mass of the spacecraft much smaller than the mass of the rocket and the field, you cannot get a velocity that is only several times at most the ejected field speed. So that's why it is very difficult to attain a high velocity for the rocket, for the spacecraft. Okay, so this is a real rocket. For the real rocket, you see most of the parts of the rocket are used for storing the fuel. The fuel are ejected out. A lot of fuel are ejected out, but you only have a very small crew capsule or surface module ejected into space. That part is much smaller in mass compared with the mass of the rocket, and that is exactly reflected in this ratio. But even with this, because of the log, you still get a velocity that is at most several times the ejected speed. So the speed of the rocket may be, or of the spacecraft may be several thousand or 10,000 kilometer per second at most. Okay. So we end this part. Okay. Now we have homework 6 released today. Okay, but the due date of homework 6 is not on today, or not on next Friday. The due time of homework 6 is on the 15th of March. Okay, that is on the Monday after next Monday, after next week, the Monday after next week, 15th of March, the Monday after next week. Okay, so you at least have a certain problem to practice. At least you can see the problem in part B where the solution is provided. Okay. Now, so we have finished the chapter on momentum and collision. Do you have any question on this part? I better stop here for a moment and to see if you have any question in mind before I proceed forward. Any questions you can think of? Now, if not, then we proceed to a new chapter on rotation. Now, rotation is actually a long chapter. So I probably would not be able to finish that whole. the whole chapter in before the midterm. And so I will teach rather slowly because rotation is something new to you. And there are some subtle concepts that requires a lot of clarification. So I prefer to teach this chapter rather slowly. Okay. Now, first, we would like to study about rotational kinematics on how to describe the motion. Okay, we do not involve the force at this moment. We simply will only try to involve the parameter that describe the rotational motion. Now, for rectilinear motion, the position of the object is described by a single coordinate, x, right, along a straight line. But for rotational motion, the position of the object is described by angle. And the convention is that we choose the angle to be the angle. There's a line joining the object and the center of the rotation. And this line makes an angle theta with the x-axis. We conveniently, in the usual convention, we choose this angle to describe the rotational motion of the object. So the x-axis is the reference direction that we count the angle. The angle is always measured in radian because we are doing differentiation and integration. So when doing differentiation and integration, we always use radian as the angle. And radian is actually dimensionless. Why? Because radian is defined by arc length, right? The arc length divided by the radius is the radian. So it's a division of two lengths. The arc length and the radius they carry a dimension of lengths. So the dimension cancel when they divide, when the two divide each other. And that's why the radian is actually a dimensionless quantity. Although it measures angle, it is dimensionless. Okay. Now we are interested in a change in, as I said again and again, the range of the midterm is from chapter 1 to chapter 6, which is momentum, right, and collision. We already announced it, and also I've written down that in the regulation of the midterm. Please take a look at it again. Okay. Now we are interested in the change in the direction, in the change in angular position. So at time t, the angle is theta, but at that time t plus delta t, the angle is theta t plus delta t. So the two angles are different. So the change in angular position will be the final angle minus the initial angle, and I denote it by delta theta. The average angular velocity is the angular displacement, the change in angular displacement divided by time taken. So I divide the delta theta by delta t. I got the angular velocity in the time interval, the average angular velocity in the time interval, and it's given by theta t plus delta t minus theta t divided by delta t. Now this is the same formulation as if rectilinear motion. The only difference is that we replace the coordinate x by the angular position theta. That is the only difference. Okay. Now the instantaneous angular velocity is just the average angular velocity over an infinitesimal small period of time. So when we take the limit, delta t tends to 0, the delta theta over delta t becomes the theta dt, and that's we call the angular velocity, the instantaneous angular velocity. So that is the angular change, rate of change of angular position at a certain instant. Okay. The angular velocity is the measure of angle per unit time. Okay, the angle divided by time, and it has a rate as a unit of radian per second. Because radian does not carry a dimension, sometimes we simplify it as per second. I prefer to write as radian per second just to remind myself that I'm measuring the angle per unit time. So although radian does not carry a dimension, when I comes to calculate the angular velocity, always write radian per second as a unit. Okay. Now, but there's another quantity called frequency. We would, in order to distinguish with the angular velocity, we call this linear frequency. The linear frequency is a number of cycle. Now, you imagine the object goes around in circle, and the number of cycle that the object go through, that object revolve in a unit time, is called the linear frequency. And the linear frequency is by definition just the number of cycle per second, right? For each second, how many cycle does the object revolve? Okay, and so its unit is per second, because cycle also doesn't have a dimension. So the dimension actually comes from the second. That's the per second. Okay. Now we also call that hertz. Hertz is by definition per second. Okay. Now, but we use hertz to denote as a unit of the linear frequency, but we never use hertz to denote the angular frequency, just to avoid confusion. If we use hertz to denote the angular frequency, that would be a lot of confusion. So for angular frequency, we always write per second or radian per second. But for linear frequency, which means cycle per second, we sometimes use hertz. Okay. And since one cycle is equal to 2 pi, right? So the linear frequency and the angular frequency, they are just related by a factor of 2 pi. When you say you revolve 3 times per second, then your linear frequency is 3. And since each turn has an angle of 2 pi, the full cycle is 2 pi. So you turn, the total angle you turn over is the linear frequency that is 3 multiplied by 2 pi. And that gives you the angular frequency. Okay, so the relation between the angular frequency and the linear frequency is simple. You have the linear frequency multiplied by the number of angle, the angle in a circle, which is 2 pi, you get the angular frequency. Sometimes we call it angular frequency, but since this is measuring a velocity, we call it angular velocity. Okay. And the angular acceleration, the average angular acceleration is the change in angular velocity divided by time taken. So in a finite time interval delta t, we have delta omega divided by delta t, and omega itself will be changing. The angular velocity itself will be changing, right? So the angular velocity at earlier time is omega t. The angular velocity at later time is omega t plus delta t. So the difference between the two divided by the time interval is the average angular acceleration. And of course, I'm going to do the instantaneous thing. I take the limit where delta t tends to 0. I measure the angular velocity over a very small time interval, which is infinitesimal interval, infinitesimally small. And so delta omega over delta t in this limit become d omega dt. And if I like, I can further express omega in terms of d theta dt, right? Because omega itself is the first derivative of the angle. So with another differentiation, the angular acceleration alpha will then becomes the second derivative of theta with respect to t. Now, you see the whole formula sum is just the same as if I'm doing the linear case. For linear case, I differentiate x, I get the velocity v. I differentiate the velocity once more, I get the acceleration, right? Now for the angular case, you denote the position by the angle theta. And when you differentiate the angle once, you get the angular velocity omega. And when you differentiate once more, you get the angular acceleration alpha. Okay, so just very similar to the rectilinear case. The only difference is that you now replace all the linear quantity by the angular counterpart. Okay. Now the angular acceleration has a unit of radian per second because you take two derivatives in time. So you have the unit of radian per second square, and you can write as radian as minus 2. Now, why do we use the angular quantity instead of the linear quantity to describe the motion? Now, that is something you learn in high school. In high school, you already have learned the rotation, the formula, the equation for uniform circular motion, right? For an object, for example, this is O. If an object is moving with a velocity v at a distance r from the origin, is revolving around in a circle, then the linear velocity and the angular velocity, they are related by in this way. V equal to r omega, all right? Now we consider we have a rigid body like this. We have a circular disc, for example. So this is the center of the disc, and the whole disc is now revolving around the center. Now we consider different points along the radius. At the center of the disc, of course, the linear velocity is 0, right? Because there's a point only with rotating. A point with no dimension rotating, that is no velocity. But for a point that is at a distance from the center, we have a velocity. And the velocity gets bigger. The linear velocity becomes larger when we are farther away from the center, right? And the velocity here will become largest. At the rim of the circle, we become largest. Because what? Because V is equal to r omega. If I have a larger r, I have a larger linear velocity. The disk, all the particles of the disk, they rotate with common angular velocity. The angle that is turned by the particle above the origin per unit time are the same for all the particles in the disk. So all the particles in the disk, they share the same common angular velocity. But the linear velocity are different. The linear velocity depends on the distance of the particle from the axis of rotation. So it is not convenient to use V, because V is different for different particles on the disk. And for rigid body as a whole, we want to have a parameter that characterizes how fast the disk is rotating. And that must be expressed in terms of the angular velocity omega instead of the linear velocity V. So that's why for a rotating object, we prefer to use omega instead of V. Okay, because omega is the same for all the points inside the rigid body. Okay, so that's the idea. Now, there's a special case. The special case is that the angular acceleration alpha is a constant, and in that case, you see that all the equation that we have derived is identical in form to the rectilinear counterpart. Okay, in the rectilinear motion, you start with x, you differentiate x, you get v, you differentiate v, you get a. And if a is a constant, then you can express the velocity and the displacement using this equation of uniform accelerated motion, right? Now you have the same thing for the angular motion. You start with the angle theta, differentiate, you get omega. You differentiate twice, you get alpha. And if alpha is a constant, then you can integrate the equation and get this equation for uniformly accelerated angular motion. So you see this equation are just identical in form to the rectilinear counterpart. The only difference is that we replace the rectilinear quantity with the angular quantity. Now, for example, here we have the initial velocity u, right? And here we have the same thing, but we write but we now are concerned with the rotation. So we write it as angular velocity. Initial angular velocity we denote by omega naught. We put a naught to denote that it is the initial angular velocity. The final velocity for rectilinear motion is v, and that corresponds to the final angular velocity omega. Okay. the linear acceleration is A, and translated to a rotation, it becomes the angular acceleration alpha. So A become alpha. Okay, that for linear motion, the displacement x. For angular case, the displacement is the angular displacement theta. So you just copy the formula. Whenever you see a linear motion with a constant acceleration, you can convert it into the angular formula by just replacing omega u with omega naught, v with omega, a with alpha, and x with theta, and then you convert to the angular counterpart. But I have to give you a warning. The warning is that this formula are true only for alpha is a constant. If alpha is not a constant, then you cannot apply this formula. Okay. Now, in the next lecture, we will have a simple review on circular motion. And after those review, we'll introduce a concept, an important concept in rotation, known as moment of inertia. And later, we will find that that concept of moment inertia is central to rotation because it's played the role of mass, of inertia of a body to change its state of motion. And that is an important idea. So we better stop here today. And if you have any questions for me, then